Welcome to the lecture 27. Today we are going to talk about the fermionic path integrals and whatever maths of the Grassmann numbers that we require. So this lecture will detail on that, and this is slightly longer lecture because I will do those maths in detail, as much detail as I can. And then at the end I will show how that relates to writing down the path integrals for fermions. Okay. So let's begin over here. So fermions satisfy the Pauli exclusion principle. That means no two fermions could occupy the same quantum state. So these are some properties of the fermions. And this simplifies several computation if I'm using the canonical quantization picture. So says that a many body system, like for the either many body system like QFT. And the reason is because the Fock space for any quantum state is just two-dimensional. Either there is a fermion, one fermion, or there is no fermion. You cannot have n equal to 2 occupation for any of the quantum states. Okay. So like boson, each quantum state of the boson is like a harmonic oscillator. You can have 0 particle, you have 1 particle, 2 particle ad infinitum. For fermions, it is just no particle or 1 particle. Okay. Additionally, the wave function is totally antisymmetric under the exchange of any two fermions. Okay. So this is all can be derived from the Pauli exclusion principle. So basically what it says that we need a mathematical setup that emulates this property of the fermions. And while doing the canonical quantization, we have come up with this thing, which is the anti-commuting operators. So let's just summarize that. For boson, which is spin 0, scalar case, and fermions, here I'm considering spin half, what we know is that the one particle state is given by, for the boson, is up to this square root of 2 AP thing. Is the AP dagger acting on vacuum will give me one particle state. Similarly, for fermions, we have that same definition. Okay, for fermions, and the is generated by A dagger and anti-fermion generated by B dagger. And the spin indices I'm not writing explicitly. Okay, and now next thing that comes, that if I act on the single particle state by AP dagger again, I will get up to some factors, a state which is 2 particle state. So it has 2 particles in the momentum state P. Right? So AP dagger square acting on 0 is proportional to 2 particle state. Now in the fermion case, what happens is that same thing, that 1 particle state if I act upon, so 1 particle state is taken from here. So if you act AP dagger again on the 1 particle state, I get 0. The reason is that AP dagger square, so this is equivalent to AP dagger square acting on vacuum is 0, and that is because AP dagger square is 0, and this we get simply because AP and AP daggers, they all anti-commute. Okay, so square of a same operator would be 0, because ideally I should have AP times AQ is equal to minus AQ times AP, and that is true even when P is equal to Q, and that basically says that AP dagger square is equal to minus of AP dagger square, and that can only be true if this operator is a null operator. Okay. The additional thing that I can have for the bosons is that if I apply A dagger P and A dagger Q in this particular order, I get 2 particle state denoted by P and Q. And if I apply these operators in reverse order onto the vacuum, I get again 2 particle state with their momentum exchanged, and that is related to the original state exactly. Okay, because the 2 particle state, one with momentum P and one with momentum Q, will remain the same. So under exchange there is no sign change, and that is because these 2 operators commute. Now for the fermion case, I have as I discussed here, its wave function is totally antisymmetric under any exchange of the fermions. So that is emulated over here by the anti-commutation of these operators. So what we have, the anti-commuting operator for the fermions, and we have commuting operators for my bosons thing. So when I take boson to the corresponding path integrals, I'll describe in the slide 2 how it actually works and what changes we need to write one thing, similar thing for the fermions. So for bosonic path integrals, we have this vacuum expectation value of time order product of phi h x1 phi h x2 is given as the path integral of phi x1 phi x2 times this exponential action divided by path integral of the exponential action. Important thing to note that on the left hand side, I have a time ordered product, an operator which is, these phi's are the operators which has commutative A's and AP's and AQ's. Okay, so this is the content of this operator, and I have quantum state omega, which is the vacuum expectation station. This is my left hand side, and that is written in terms, in the path integral formalism, it's written in terms of these path integrals of this real and complex numbers. Okay, and of course, for any real and complex number, the product of these two numbers is commutative, and that is kind of reflects the fact that AP's and AQ's are actually commutating operator. If AP's and AP Dagger, with the momentum level being same, they have a non-trivial commutator owing to the chemical commutation relation between them. But other than that, they are completely commuting objects. Okay, so what is done over here is that they are expressed in terms of Gaussian-like integrals over real or complex numbers with commutative products. Now, for the fermionic case, if I do exact same copy, then what I have, that exact same thing I have on the left hand side, my time ordered product, my vacuum quantum state, and the operator psi h x1 and psi bar h x2, they are written in terms of anti-commuting AP's and AQ's. Okay, on the right hand side, I'll just copied it, the bosonic formula. But in order to emulate the anti-commutation properties of AP's and AQ's, what I need is that this psi x1 and psi bar x2, they have to be numbers, much like complex and real numbers, but they have to have special properties. They should be anti-commuting numbers, so such that A times B is minus of B times A. Usually this happens with the matrices and operators, but I need that for numbers. These are numbers that over which I have to perform an integral. So what we need is anti-commuting number and a self-consistent algebra to be able to define arithmetic algebra and calculus. We need this. Okay, and the set of rules is given on slide 3, where I introduce such an object. So this is called the Grassmann numbers. So let xi, yi, and zi be the set of real and complex numbers, and eta i's and theta i's will be the set of real or complex Grassmann numbers. So we start with the real Grassmann number and we'll come to the complex one later, but the properties will be satisfied, same properties will be satisfied for the complex guys as well. So the property, the most important property, is the first thing written here is theta I theta j is equal to minus of theta j theta I, theta I theta eta j is equal to minus of eta j eta I. Okay, this is just second part was, it's not really required to say this. So this is the anti-commutative property. So two Grassmann number must anti-commute with each other. The second property is theta I xj is equal to xj theta I. So it commutes with the ordinary numbers, real or complex. And secondly, owing to this first condition, is theta I square equal to 0, since theta I is equal to minus I theta I, minus of theta I, using this relation, put I equal to j. So this is these numbers are nilpotent. And secondly, theta I theta j multiplied by theta k is same as theta k multiplied by theta is theta j. So to say, any doublet of this number, any couple of this number theta a theta k acts like ordinary number as far as the commutation relations is concerned. What is happening that I am taking theta k 1 across theta j, giving me a minus sign, then again another across theta I, giving me another minus sign, giving me this number without overall sign. Okay, so it as if this theta I theta j acts like a real and complex number, but don't be fooled over here. They still have special property of being a Grassmann number, because if I write theta I theta j to be some x, then x square is 0 again, because x square will have 2 of theta i's, and then I can use this relation. Okay, so even if this is acts like a real or complex number, those real or complex numbers are going to be nilpotent. The square of that number is going to be 0, even if they are commuting numbers. Okay, so this, I can create a commuting number with 0 square nilpotent number if I can write that number as a product of two Grassmann numbers. Okay, so these are the basic properties. This is all we need for defining, and we'll define the calculus later. But let's just say before going to a calculus, I have to first define what kind of functions I can have of this Grassmann number. So let's say f is a map from the Grassmann set of Grassmann numbers or to a complex number. Okay, so f of theta is some x plus eta theta, where eta and theta are the Grassmann numbers and x and y in this here y is written elsewhere, x and y are going to be a complex number. So why I stop over here? Because if I do a Taylor expansion near theta equal to 0, first thing I'll get is a constant term, which is x. Next time I'll get a first order term, theta, and since the overall map is to a complex number, so it must be multiplying with another Grassmann number to give me a complex kind of number over here. The next term would have had a theta square in it, but since theta square is 0 for Grassmann number, so here my series ends. It's much like my Fock space for fermion being only 2 dimension. Here I'm saying that the Taylor series having only 2 terms. Okay. Now I can have another function g which takes a number from Grassmann variable set and maps it to another number on the Grassmann set. So g of theta, I can have a function like eta, which is a Grassmann number, plus x times theta. X is a real or complex number. The next term in this series could have been a theta square term, but then again that is 0 theta square, so all the higher order terms are absent over here. And then I'm becoming a bit desperate and saying that this h is a function which takes a Grassmann number and maps it to some linear combination of a Grassmann number and a complex number. Here h of theta is equal to x plus y theta. So first term is bosonic, so to say ordinary real number. Second term is y times theta. It is the fermionic or the Grassmann type. Okay, but we can easily say this one is a desperate construct. Usually such mixing is not allowed. I mean, there's nothing wrong with writing it mathematically. I wonder wait up here. So just for completeness, I'm writing this. Another thing that I start with a complex number being a variable, and it maps to a Grassmann number. So let's say psi of x is a fermion field like psi of x. So my return value is a Grassmann number, but the x, the field on which it depends, is a real or complex number. So it can be written as some, it is not really an expression for the field, but this is just this kind of function where eta plus x theta, where eta and theta are Grassmann number and x is some real number. So I can write functions like that. Okay, but most of the functions that we use in physics are either of the first kind, where the variable is Grassmann but the return value is real or complex, or the fourth kind, where the return value is a Grassmann number but input variable is a real or complex. So for example, here the Dirac spinner is mapped from r to the power 4, it's a 4-dimensional real number, which is the value of x muse, to a Grassmann number. Okay, so this is a fourth kind of function, and my Lagrangian is takes 2 of the Grassmann number and some real or complex number, maps it to real number. It's the first kind of function. Okay, so we can have the value of the function to be ordinary or Grassmann, with the input variables being a combination of Grassmann and complex number. Okay, so of course usually when we have map, it is some set A cross set B going to set C. So here what it says that the return value has to be either an ordinary number or a Grassmann. Don't try to have this desperate construct, the h function that I have written over here. Usually that doesn't appear. Okay, I'm just writing it for completeness. If somebody defines this function, the calculus on this function is very well defined. Okay, but usually it doesn't appear. It much like saying that you dimensional analysis kind of stuff, you don't add length and a mass or something like that. Okay, so let's consider a function of multiple variables. For f of f is a map from g to the power n to complex number, and for various s. For n equal to 1 Grassmann number we already discussed. Okay, so f of theta is x plus eta theta, theta square is 0, so it's done. So these x and eta are constants. For n equal to 2, for 2 Grassmann variables, the most general function is x naught, okay, plus eta 1 theta 1 plus eta 2 theta 2. So eta 1 eta 2 are Grassmann numbers, plus x2 times theta 1 theta 2. Now next term would be a theta 1 square theta 2 or theta 2 square theta 1 or further higher, which will have higher power of either theta 1 or theta 2, and since this is 0, so here our Taylor series of 2 variables stops. So here all the xi's are complex number and all the eta i's are the Grassmann number, and they are constant. The variables are theta 1 and theta 2. And for n Grassmann variable, I'll have, you can see that x0, then eta I theta I, then xij theta I theta j, and eta ijk theta I theta j theta k, and so on. Here I'm using convention that I is less than j is less than k while writing this product. The last piece in this expansion would be a product of theta 1 theta 2 all the way to theta n, and its coefficient is some phi. So here all the xi's are complex number, all the eta i's are Grassmann number, but the phi is a complex number if n is even, and it is a Grassmann number if n is odd. Okay, because the overall return function has to have even number of Grassmann variables. If n is odd, then phi has to be a Grassmann number, otherwise it has to be a real or complex number. So this is a variable of the function of n variables. Okay, so likewise we'll use. Now, as I said, we can also write the complex Grassmann number. So any two Grassmann number can be combined to give a complex Grassmann number, like, much like the case of real numbers. So theta is theta 1 plus I theta 2 by root 2, and theta bar, which is defined as theta star, is theta 1 plus I theta 2 by root 2, the complex conjugate of this. And so involution, the so-called convex conjugation, is defined as theta eta star is eta star theta star. This is the definition, and which is minus of theta star eta star, because these two are also Grassmann numbers. So where star means this complex conjugation, or ideally one could write bar, because while writing Grassmann number one doesn't use this star notation but uses the bar notation. Okay, and one can treat either theta 1 or theta 2 to be theta 1 theta 2 to be the independent variable, or theta and theta bar to be independent variables. So basically we'll have theta 1 theta 2 going to d theta and d theta bar. So Jacobian of this transformation is 1. Okay, and if I have to write a function of theta and theta bar, it exactly like the two variables over here. Okay, so here I'm writing x0 eta bar theta and theta bar eta plus x2 theta bar theta, and I'm using a convention that the complex conjugate guy is standing on to the left. So now, having defined all these things, we can move on to define what would be the derivative of this function. So one can have either the left derivative or the right derivative. So by convention I choose them to be 1 in this particular case. So d theta by d theta is 1 when it's acted from the left. So remember, theta is a Grassmann variable and d by d theta is another Grassmann variable. So it's important which way they are organized, and the derivative is defined with this convention is that d by d theta acting on theta from the left is 1, and d by d theta acting on theta from the right is also 1. So this is my convention. The product rule is d theta acting on x times theta is dx by d theta times theta plus x times d theta by d theta, where x is a complex number, a real or complex number. Okay, and so this is my standard Leibniz rule for taking derivative of the product. And when I have d by d theta of eta and theta, where eta is a Grassmann number, then I have operator acting on eta from the left, because this is for the left derivative. So d eta by d theta times theta, and then the derivative crosses the eta to act on theta, so there it picks up a minus sign, so minus eta d theta by d theta. So this is important to keep track whenever these numbers or the derivative cross each other, so they always pick up a negative sign. If f of theta is x plus eta theta, then the left derivative will just, x is a constant, so it doesn't give anything, is the d theta of eta theta as given from here. And since d eta by d theta is also 0 because eta is a constant, so I just have a second piece which gives me minus eta. Okay, and if I do the same thing with the right derivative, you can just perform all the steps. Now here d theta, the theta times d theta acting from right on theta is 1, so I just get the answer eta. Okay, so the left and the right derivative of general functions can be very different. Here it is just up to a sign, but general functions can have different number of different variables and different positions. So the left and right derivative in general are not just overall sign, but it could be very different from each other. Now I know how to take derivative with regard to a Grassmann number. So let's assume that my Dirac-Lagrangian is written in terms of this Grassmann number. So my size and psi bars are Grassmann number. Okay, so I use exact Euler-Lagrange equation of motion, and if I perform the task, so the first left hand side, if I had to take the del L by del with regard to del mu psi, so del mu psi is my Grassmann number. So I have to take this derivative with regard to that across psi bar, so that picks up a minus sign, and then it acts on this del mu psi to give me 1. So I get an answer minus I psi bar gamma mu. Okay. Now on the right hand side, the same thing. The del by del psi has to cross psi bar to give me this. So it kills the sign over here and gives me m psi bar. Interestingly, it so happens that even if I took a psi and psi bar to be ordinary real or complex number, my equation of motion will still be same. And the reason is that this crossing of the derivative term is happening same number of times on the left hand side as on the right hand side for this simple Lagrangian. If the Lagrangian has higher order polynomial in size and psi bars, then this simple thing will not be true. So in general, it may not be true. I shouldn't say it will not be. In general, it may not be true. And so we have to be careful about deriving the equation of motion. So we have to treat, we have to make a call and treat them as a Grassmann number. Okay. So after having discussed this, let's move on to the integration of the Grassmann numbers. And so integration have to have certain property. First of them is a linearity. So d theta integration. So this is what I want to define. So d theta integration of x1 f1 theta plus x2 f2 theta will be x1. So this x is a constant. X1 d theta of f1 theta plus x2 d theta of f2 theta. So this is the linearity property where x1 and x2 are the complex numbers. Okay, and another property that we need is a shift of variables. So f of theta, integral over d theta f of theta is same as some d theta twiddle f of theta twiddle, where theta twiddle is theta plus some eta 0. So if this is a shift of variables, then d theta twiddle is just d theta. So no Jacobian of transformation, so to say. So LHS, if I have to write from this this equation, so d theta f of theta we have already okay, we haven't computed, we have to compute. So will be this value, and using the linearity I will write it is same as well, x I should have written outside, so but let me just keep it like this. So it is integral of d theta times x plus integral over d theta times eta theta. This I will get from the left hand side of this expression, and then using the fact that d theta twiddle is nothing but d theta, and here in f theta I will replace theta by theta twiddle by theta. So I have the RHS as integral over d theta of x plus eta theta and eta 0 if I put value of twiddle. So I collect all the constants together, which is integral of d theta of x plus eta naught plus integral of integral over d theta eta theta. So if I compare this guy with this guy, okay, the only thing is that the constant will always go outside the integral. So this first term must be equal to this first term, and the only way it can be equal for a general eta naught, eta and eta naught I should say, is when integral over d theta is 0. Okay, to make the first term consistent. So integral over d theta times any constant must give me 0. So that is one result I get out of linearity and invariant under shift of variables. But second guy doesn't have to be 0. The eta can come out of the integral, and that's a matter of detail. So here by convention one sets that integral over d theta of theta is equal to 1. This is the convention. One sets the convention. It has to be non-zero, so let it be 1. Okay. So given that, I can do this integral of d theta f of theta. So first term will of course gives me 0, which is the constant piece, and next piece just gives me d theta eta theta. And then I can consider this two ways, that eta is moved to the right giving me a minus sign, or eta is moved across the d theta outside the integral sign giving a minus sign. So it gives minus eta times integral d theta theta, which is just minus eta. And we note that this result is exactly the same if I took the left derivative of f theta. So integration is same as the left derivative, and we'll see it is for multi-dimensional case also. And if I have multi-dimensional integral, then I'll have integration over d theta 1, integration d theta 2 of theta 2 theta 1 in this particular order. So of course this integral sitting in between is equal to 1, so that it goes away. It's just the ordinary number 1. Then we have integral over d theta 1 with theta, that also is 1. Okay, so this way we will compute the these guys integrals. And if I have this theta, so remember here theta 1 and theta 2 are there, and the product of thetas that is appearing over here is in the reverse order. Okay, but if there it is not reverse order, then I have to put into the reverse order, and if it requires odd number of swaps, then the result will be -1. So like here d theta 1 d theta 2 integral of theta 1 theta 2 will be -1. Okay, so let's do the integral of two-dimensional integral of this function of two variables that we described in a couple of in the previous slide only, sorry, a couple of slides ago. Function of two variables. So here I can have several terms, which is d theta 1 d theta 2 of x naught, and that is 0 because d theta 2 of any constant is 0, and then d theta 1 of that 0 will be 0 anyways. The second term has eta theta 1 into it. Okay, so what I do, I bring this theta 1 across two of this Grassmann variable to sit over here. It becomes d theta 1 of theta 1, that is 1, but d theta 2 of eta 2 or some other constant, if eta 2 is sitting outside, is again 0. So this second piece also gives me 0. Third piece has d theta 1 d theta 2 of eta 2 theta 2, and again I can do the integration of theta 2 to give me -1 because it has to swap the order, and then the integration of theta 1 over a constant is 0. So that third piece is also 0. Only non-zero piece is the fourth piece. Okay, where I have to take this x2 outside and then put theta 1 theta 2 in the correct order. That gives me minus sign, and that all this integral, as we said above, is 1. So whole thing is just minus x2. Okay, so d theta 1 d theta 2 integral of f theta 1 theta 2 is minus x2, and incidentally that is exactly the same you will get if you take the derivative of this function, left derivative of function, in the same order as the integrand are done. So you have d theta 1 d theta 2, here you have to take derivative with regard to d theta 1 and then d theta 2, or rather first regard to d theta 2. So d theta 2 is sitting on the right hand side. Okay, and if I have function of n variables, which is just repeated from the previous slide over here, and I take the n variable integration over here. So of course all the places where all these variables are not present, then that particular integral is carried over a constant giving me 0. So only non-zero contribution here will come when all of these variables are appearing in the term, and that is my last term. So that will be phi n. Now I need all the numbers to permute to be in the same order. Okay, so since my integration is theta 1 theta 2 all the way to theta n, and variables are also in the same order, if I have to put it back into the reverse order, that will give me a factor of -1 to the power floor of n by 2. Okay, that you can confirm. But whatever is this expression, important thing is that if you take the derivative in the same order as these integrands are sitting, the result will be same. And the reason is that d by d theta of theta is 0. So if I consider d by d theta as an operator acting on theta, that gives me 1. And integral d theta is also an operator acting on theta, giving me 1. So they are doing the same task basically. Okay, all I have to do is just bring theta next to the corresponding operator, and in order to do that I have to perform same number of permutations both for the integral and for the derivative. So this integral is same as this derivative, whatever value it may be. So for exact value computation I have to compute exact number of permutations that it has gone through. Okay. So with this setup of derivative and the integrals, we start moving towards the kind of integrals that we are interested in, which is a multi-dimensional integral of exponential function. So we start with the two dimensions. So the integration of theta 1 theta 2, integration over theta 1 theta 2 of exponential minus theta 1 x theta 2 can be written as that you just expand the exponential, and of course the exponential will have the 0th term, the first term. The second term will require theta 1 square, so those and higher order terms are 0. So this is the expansion of exponential exact. Okay, and here if I perform the integral of the two dimension as we saw earlier, the first term gives me 0 and second term has a minus sign, but then theta 1 theta 2 are in the opposite order, so it basically gives me x. Okay, now if I change the variable from theta 1 theta 2 to a complex variable, the same result holds, because nowhere I assume the reality of theta 1 and theta 2. So theta and bar and theta I write, and same set of things I will perform, and I'll get same result x. Okay, now if I have to compare this with the corresponding Gaussian integral in the complex number, so integration of d theta dz star of exponential minus z star xz, that will turn out to be pi by x. Remember, there are two variables over here, so it is a square root of pi by x, so basically pi by x. The important thing to note other than this factor pi is that the x that was sitting over here appears in the integral, and here that x that was there appears as the inverse over here, 1 over x that sits over here. Okay, now if I have this theta bar multiplying the exponential, so this is like creating the second moment, computing the second moment of these thetas. Okay, so again I will expand this exponential multiplied by theta bar from the left hand side, and of course when that multiplies with this piece, that will be 0, so only thing that contributes from the exponential is 1. So this is my integration, which is nothing but 1 can be written as this x multiplied by 1 over x. Why I'm writing this is because if I do the similar computation, the second moment if I'm computing for the Gaussian, what I get is pi by x multiplied by 1 by x. It is like this guy multiplied by 1 by x. So as far as this behavior is concerned, that if I have a second moment, I get 1 over x times the 0 moment case, that behavior remains same. Okay, but the fact that what is the value of the integral, that changes because this x appears in the numerator as against here is in the denominator. Now another thing, that if I have this exponential of n variables, okay, integration of all those n variables of this exponential minus theta I bar bij theta j, okay, so this turns out to be determinant of b, as against for the complex number. If I did the same thing, it was a pi to the power n divided by determinant of a. Actually for real numbers it was square root of this, but for complex number it's twice that integral for the real and imaginary part. So I'll get two such factors, and so basically it becomes pi by n determinant of a. And remember, there is no 1 by 2 factor over here, that's why it is not 2 pi to the power n. Okay, now this particular fact that how this b comes out as a determinant b, you can already get a hint from here, because this theta bar x theta returns me x over here rather than 1 over x. So here also the similar situation is there, and in the real number or the complex number case it was 1 over determinant of a. So here I should have gotten determinant in the numerator, but there are better ways to see it. There are two ways one can try. The first way is just same as how we did here, by changing the variables. Okay, and change of variables require Jacobians, so we'll discuss it in the next slide. So if I use the change of variables, make it diagonal, then it is just a bunch of this integral of this kind. So it is a product of eigenvalues, which is just a determinant, so it's nothing big deal. But the second and more complicated way slightly is to see is that you expand this exponential function. It has only n plus 1 term. First term is just 1, and then n power of this, because n plus first power will have at least one of the thetas repeating. Okay, so the last piece with the n plus 1 piece that will contribute has minus 1 to the power n divided by factorial n, that is coming from the exponential term, and then theta bar I1 bi1 j1 theta j2 j1, and then same thing for I2 j2 and all the way till in jn. And if I write this, and there is a bunch of integrals, so what is the purpose of this integral over, like here, integral over d theta and theta bar and d theta of this any of these variables, is that it brings up a sign. Okay, all the integrals are actually 1 as long as these variables are staying next to each other. So the purpose of this integral is to bring an appropriate sign, and we use this definition of the determinant of any matrix is 1 over factorial n epsilon I1 I2 all the way till in, and epsilon j1 j2 all the way till jn of b1 j1 b2 j2 all the way till bn jn. Okay, so this is the determinant, the definition of the determinant that is used over here, because here the integral does nothing but basically give you a this Levi-Shifter symbol, overall sign. Okay, so what I'm saying is that this epsilon comes from this various integrals by performing the by the means of the permutations. Okay, so that is what all these things will give, all these factorials and all these things, all these signs, everything will be absorbed. Okay, and we'll have just determined B as my answer. So this is to actually see how it works, may require you to think carefully. But if you don't want to do that, then you use exactly what you did for the real complex number, is to diagonalize this matrix Bij. Okay, and then look at that. But we already see that for Grassmann numbers, the determinant will sit in the numerator, not in the denominator. Okay. Next thing, as I said, we'll discuss the change of variables, and that here also we have very strange property. So let's say theta twiddle is some eta naught plus y theta, and I have f of theta, the function for one variable is x plus eta theta. So what I have is d theta integral of f of theta, which is should be same under this variable change of variables, is d theta twiddle f of theta twiddle. I should have had this. So it's just a name of variable, right? Because theta is integrated over dummy variable. So just by renaming theta to theta twiddle will not change the value of the integral. And this is equal to minus theta as we computed earlier. Now what I do is compute integral over d theta of f of theta twiddle. Okay. So what it is integral over d theta, and just write theta twiddle and expand it. Of course, the first piece being constant gives me 0, and second piece gives me y times eta with a minus sign. Okay. So what? So this is one result I have. At the same time, I can write integral over theta twiddle of f theta twiddle is equal to this number, okay, which is this guy, divided by 1 over y. Okay. So this integral is minus y eta, and this integral is minus eta. So the difference between them is just 1 over y. So I just write this thing, okay, and take 1 by y inside. Usually what happens, that what is y if you look at, if you just take a thing here, it is d theta twiddle by d theta. If you compute, you will get y. Okay? So this is how the Jacobians are computed. So what I am getting is d theta twiddle of f theta twiddle is equal to d theta times d theta twiddle by d theta inverse times f theta twiddle. Usually what happens that if I have for ordinary complex number is that dx twiddle fx twiddle is, then I put dx and divide by and multiply by dx, and then this is my Jacobian. Here exactly inverse appears in the case of Grassmann numbers. Okay, so there are a couple of differences here when I'm doing with my calculus with the Grassmann number, that my integration is same as the differentiations if you perform the same order. If you have multidimensional Gaussian, then the determinant of the matrix sits in the numerator, and if you have change of variables, the Jacobian is inverse of that. But it doesn't matter for the case when the Jacobian, when your transformation Jacobian, if you're doing a transformation using a simulated transformation or some orthogonal transformation or unitary transformation, because determinant of those guys is 1, so whether it is sitting in the numerator or the denominator would not matter. This Jacobian thing would matter when we are doing a path integral for the gauge bosons. Okay, interestingly, for the gauge bosons you will need some of these things. Now, having played with this Gaussian integral, you remember when we are talking about the Gaussian-like integral, we had this generating function for all the moments. So let's just write my generating function z of eta I and eta j bar. So these are two vectors. Okay, I could have written eta vector and eta bar vector, and this product of this integration of all the theta i's and theta j's, the theta bar, theta and theta bar, and exponential minus theta bar I bij theta j, much same as what we did in the previous slide. Then I added this source kind of term. Okay, what for the scalar case I have j times x, here I have eta bar times theta and theta bar times eta. Okay, sum over all possible i's. Now if I have this definition, then all I have to do is do this change of variables, where theta twiddle is theta I minus b inverse of ij eta j, and theta bar is theta bar I is theta bar twiddle I, or theta twiddle bar I is theta bar minus eta bar j b inverse ji. Okay, if I do this transformation over here, what I do is that first of all, the Jacobian of this transformation is the Jacobian matrix is identity matrix, so determinant modulus of that will be 1. So I can just my measure of integration is same, and the integrand, if you do this transformation, becomes one thing which is independent of theta totals and other piece which is dependent on theta total. Okay, when I perform the integral, of course the first piece, interdependent piece, which has b inverse eta ij, will come out like this, and and this guy is anyway determinant b, so you just write it like that. Now interesting thing, since it's a generating function, I have to take the derivative. So if I take minus del by del eta L, okay, so why I'm doing minus is because if I take del by del eta L, then it has to cross this theta bar to act on eta, so it will give a minus sign. So I'm putting minus sign over here such that the returned value is just theta bar L. Okay, same for del by del eta bar k will return me theta k. Okay, if I take derivative like this, then basically I'm asking for this particular moment. Okay, I want to compute this particular moment. But if I take the same derivative on this z, of course determinant b is a constant as a function of eta, so I just it will give me this particular guy. Okay, and taking derivative of this particular guy, actually I forgot to write this, not just determinant b but determinant b times this entire exponential factor will also sit over here. So let me just make that correction, times exponential of eta bar b inverse eta I j j. Okay, this will also sit there. And what is this? Determinant b is nothing but when when both the eta and eta are set to 0. So if I and when you set etas to 0, this factor will become 1. Okay, so what is my expectation value is just the inverse of this. So this looks like a propagator. Okay, so what I said over here, when you take the moments, the behavior that moments actually just bring the inverse of whatever sitting over there, that property remains same between the bosons and the, so to say, the complex number and the Grassmann numbers. What changes is the value of the Gaussian integral. Okay, so Gaussian integral has determinant instead of 1 by determinant. That's the only change. So moving on for completeness, that if I write the Dirac field with source, the partition function for that, then z eta x eta bar x would be path integral over psi bar x d psi bar x d psi x of exponential I times this minus t to plus t d4 x psi bar I gamma mu del mu psi m psi bar psi plus eta bar psi bar eta. Okay, so these are the etas are introduced, and if I complete the square, do the change that we did in the previous thing, I'll get exponential minus d4x d4y of eta bar y s x minus y eta bar x multiplied by z0 0. So this is the thing, is a propagator for the Dirac field. So here I have this field, this guy which is sitting over here as a matrix between psi bar and psi, that is I del slash x minus m acting on s x minus y is I times delta 4 x minus y. This is my Dirac equation, Green's function for the Dirac equation. So the inverse of this, if I put back into the expressions, this is my partition function for the free Dirac theory that will go. So obviously, if I, in the presence of eta, if I want to write vacuum expectation value of psi x, and that will be proportional to I times delta del by del eta bar acting on z. So this is in the presence of eta. I'm not setting eta to 0. That because, you know, if you want psi, you have to take derivative with regard to eta bar. Now when you want psi bar down here, you have to do the derivative with regard to eta, but eta has to cross the psi bar. So here the signs will be opposite. So here minus I is just to kill this I, and here I have to multiply by I, because other than killing the I also have to kill the minus sign, okay, to get this guy. So basically wherever you see psi x, you replace it by minus I del by del eta bar, and wherever you see psi bar, you replace it by minus del by del eta I times. Okay. And for the scalars, both the phi and phi daggers had the exact same thing, which is minus I del by del j dagger for the phi, and for phi dagger minus I del by del j. So there is no sign change that was there, only For this field, you have J dagger, and for the field dagger, you have J. Okay, that's for the scalars. So 2-point correlation function for in the path integral formalism for Dirac field would be just 1 by z00, and these derivatives acting on z eta bar, and then you set eta equal to 0 equal to eta bar, and so on. All other things you can compute from here. With the current setup, we can handle any number of scalars and fermions, but without any interaction, because we have not talked about how to discuss how to deal with the interaction. That we'll do after discussing the gauge theories. Okay, so we'll discuss the all kind of interaction in one go. But after having done this fermion thing, so main step beyond scalar fields that was required for the function integral method for the fermions is the invention of these Grassmann numbers, and to use them in a self-consistent manner. Okay, so with this I end this lecture, and the next lecture will talk about how do we quantize the gauge theory. We'll start with some ideas that why we need to be careful, and which we have already discussed in the while discussing the gauge theories, quantization of the gauge theories. And here we will see if I can do if one can quantize a non-abelian. So we'll start with the non-abelian first, because it has more issues, and then abelian case is just a subset of that. So I will start with the non-abelian and quantization, do all the mathematics required for that, and then take abelian as a special case, and we'll do the gauge fixing and various things over there. Okay, so with this lecture 27 comes to an end. See you in the next lecture for gauge theory quantization using path integrals.